All right, everybody, thank you for tuning in to GPDIS 2020. We have a fantastic round of presenters today. First on the bat is Jennifer Herron. Jennifer is the CEO and founder of Action Engineering, which is a registered women-owned small business that specializes in guiding organizations through their transformation into model-based enterprise using model-based definition. She also serves on the board of directors of the Digital Metrology Standard Consortium, or DMSC, which maintains the QIF and DMIS standards. Jennifer has extensive experience in this space, and I will let her continue her bio. But before that, I want to thank all of our sponsors for GPDIS. Without these companies, this probably would not be possible, so hats off to them. Anarch, Cupids 3D, Transmagic, Boeing, SimData, Elysium, Northrop Grumman, Parker, and PDES. Just a quick recap on the history and focus of GPDIS. It stands for Global Product Data Interoperability Summit. It was formed in 2009, and it was a consolidation of two conferences, the Data Exchange and the SOA Deep Dives, addressing integration technologies along with non-proprietary exchange of data. This year's 2020 theme is the Great Race of Digital Transformation. Together we will explore digital transformation and what it will take to fully achieve it. Using the Great Race as a metaphor, we will explore the building blocks of digital transformation and how interoperability will enable the digital transformation journey for industry.
All right, you ready for me?
Yes, I will pass the ball off to Jennifer. Take it away, Jennifer.
Hi, everybody. My name is Jennifer Herron, and you may know me as the founder of Action Engineering, but I am also the ASME Vice Chair. But today, I'm here to represent the Digital Metrology Standards Consortium, or the DMSC. I am on the board of directors for the DMSC, and I do believe that Curtis Brown is also joining us. And is going to be available for questions afterwards. So as we go through the presentation, I'm hoping you'll write us questions in the chat window, and maybe Curtis, if he is able to answer in line with my presentation, he can answer, or I think we're going to have plenty of time at the end for some live Q&A. So today, one of the biggest pain points I hear regarding drawing or model data is when changes are needed in the original engineering, it takes a lot of time and money to rigorously make, control, and propagate those changes to downstream users. And we all know that changes are especially costly after the product is delivered. So anything we can do to prevent changes after delivery is a really big win. When leveraging digital data, we have the opportunity to reduce cost and time while making those changes, while controlling them, and while propagating them to downstream users. How do we do that? Well, we use the tools we have at our disposal today to control the digital data. So I had this idea that I proposed to this group of experts you see on the screen, and I asked them, what would the data look like if we use QIF to track changes? And, you know, being a skeptical engineer, I wanted to see the actual code and walk it through so that I could actually trust the digital data. So these fine folks collaborated with me to prototype what happens when we make engineering changes captured in the native CAD models, and then propagate those changes to downstream systems, such as inspection. We did this all centered around using the QIF framework. By the way, these companies are also members of the Digital Metrology Standards Consortium, or DMSC. So here's a part I created to create a prototype. I like to work on parts that are realistic and provide complex geometric tolerances because I always learn more when I apply model-based definition to real-world parts. So this gas turbine engine blade proof of concept traces engineering changes using QIF. I like to tell stories, so let me tell you a story about how the work is traditionally done today. Here's Tyler. He's our designer. He models up the engine blade that he passes on to his analyst, who, for an airfoil, performs computational fluid dynamics. And then that model moves into the product definition phase, where the model is tweaked, finalized, and detailed to capture the engineering requirements for manufacturing and quality. Then a drawing is created to document tolerances, notes, and manufacturing information. That drawing is then passed off to the shop floor to be manufactured. And the reality for many supply chains is that another 3D model is actually generated from the drawing to feed the manufacturing process steps. So we know that any new airfoil design requires a first article inspection. So inspectors then balloon that drawing to create human-readable IDs used during inspection, and then the part's ready to be delivered. With the digital tools that we have available today, we begin to understand that we might have a lot of waste in our drawing-based processes. What I mean by waste is the part is often remodeled from the drawing in order to build in-process models or operation worksheets or work instructions. And if we leverage the engineering product definition to seed the manufacturing definition, then we can eliminate the error-prone remodeling that occurs today. On average, a quality planner or programmer will spend about 8 hours per drawing sheet to balloon and program a coordinate measurement machine for first article inspection. So if we leverage the engineering product definition data again to create the CMM program, then we can eliminate roughly 60 to 80% of time spent in the quality department. And you may even be able to increase the throughput of your parts into the inspection department. So if we can utilize the initial product definition model to seed manufacturing and quality 3D data, then we can eliminate human error and time spent on these 3 steps here. So I know most of you are aware that companies have been successful and realized business value with model-based definition or MBD data during new product development. But I had to ask the question, what happens when a change request and change report are needed? So let's take a look at that flow here. So Tyler makes revision B of the airfoil. CFD gets rerun on revision B. The product definition is altered to reflect the changes requested to open up the tolerances. The drawing is revised. And now we know that it's likely a new manufacturing model will be needed. And then, of course, quality balloons the revised drawing again. So if we can optimize engineering changes and evaluate the digital flow of data at a discrete machine-readable level, then we can realize the savings again. So even after the initial release of a new product, so we're actually leveraging those savings again in engineering changes. A significant pain point I often hear is around managing and controlling engineering changes from the design organization to the supplier who builds and inspects the part. So if we can streamline the revision steps by leveraging digital handoffs of data, then the data can flow easily to the supplier, and we begin to reduce the pain points in the supply chain around engineering changes. And most importantly, to you as the design organization, you may be able to purchase parts from the supplier at a lower cost, and I have seen that happen. I know I just gave you cartoons for this concept. I like to kind of put my money where my mouth is, so I'd like to back it up with some real data and real code and give you an idea of what that looks like to have revision A and revision B. So when I brought this problem up to my colleagues, they helped me understand that one of the barriers to trusting digital is that when we create a coordinate measurement machine program, CMM program, for revision A, we really don't want to recreate that program for revision B. So what do? This was kind of the problem we were diving into. Because not only does that recreation add time and money, but we also lose the traceability of the data. Okay, this is Enter QIF and my colleagues who helped me figure out this process. If this is the first time you've heard about QIF, I apologize for not explaining more about the DMSC standard, which happens to also be an ANSI and ISO standard for Quality Information Framework. At the end of this presentation, I do have some more slides about that, and I'll bring that up and we can talk about it more then. And we do have Curtis Brown, who's on the line, who can help us look into that as well. So I'm going to dive really fast right into what a cupid is, and this is the basic building block data element of QIF. It is a universally unique identifier, and it is the building block of everything, and we can add a characteristic to every single characteristic in the model that we see. So what you see on the screen is a unique identifier for the QIF file. And then this 3178 ID is appended to that file, and it represents the collection of surfaces for the 0.08 profile. And we have the ID 2022, which represents the surface profile characteristic. So one is representing the geometry features and the other is representing the surface profile. So solving the problem here, revision A to revision B, you'll kind of notice that we have to do things a little bit differently. In revision A, we've got a native model, we publish a QIF file, we simulate the inspection. Then in revision B, we'll make the changes in the native CAD file and then we'll republish it. We will do a validation step to create a was-now report for revision A to revision B, and then we'll update the inspection. So I'm going to show you that a little bit closer and what it looks like in the real code. This is our native model. And we are going to take a look at the native CAD model and then create a QIF file. And it always seems kind of anticlimactic because you just sort of click two buttons and then you have a QIF file. So now that we have that QIF file, let's look deeper into the code itself. There's a lot going on the screen right now, but we're primarily looking at GP9, which is the characteristic for the surface profile 0.08 and its associated collection of surfaces for the base of that airfoil. So 3178, remember I showed that to you in the UUID. We track that into the 2022 surface profile identification, and you can see that those are connected and related together. And then the 2021 ID contains the actual value of 0.08 of the surface profile. So this page that I'm showing you right here, this is the engineering requirements captured directly from the native file in a QIF file. Okay, so then it's time to do the fun part of CMM programming. And remember I told you that every drawing sheet typically takes about 8 hours to perform the ballooning steps and then also to create the CMM program. So here we are making the selections to generate a CMM program. And the first thing it's going to do is a collision detection. Didn't find any collision detections, that's great. We'll kind of take a look at the program and review it. And then we'll run the simulation. Next step, actually measure the part. So that's what happens after the DMSC program is generated, put onto the appropriate CMM machine that you need. Okay, once we have measurement results, we're able to actually view on the 3D model the requirement for that surface profile, and we can also see the results as well. So looking into the code and how QIF actually captures and measures those results, I will point out we have created a new ID to capture actual measurements, and that's 3319 here. And there's our actual measurement result captured in the QIF file. And then notice that we still have the 3318 to identify the collection of surfaces for the base of that airfoil that we're representing, and then also the ID 2022 that has the surface profile definition. Okay, that was all revision A, right? So we did all that work on revision A. Now we want to make it as easy as possible using the digital data that we have available in revision B. So dive in a little bit deeper into there. Here's the revision B model. I've made the necessary changes. I opened up the tolerances because, you know, there's always somebody who needs more tolerance. And then we update the QIF file. And instead of making a new one, we create a revision. Again, sort of anticlimactic with just a couple of button clicks to get that updated revision. Now, I also know that a best practice with digital data and any model-based definition data is I want to run a validation report. So I run a validation report, and one of the reasons I love these validation reports is that I can see that on the left, I have a 0.05 tolerance, and on the right, I have a 0.07 tolerance. So right away, an identification is made automatically without me having to spend a lot of time on that report, manually generating it. And I've got my revision A to revision B captured and documented. Okay, so then we update the CMM program using that QIF file, rerun the simulation, take our measurement results. So what's really interesting here is that we have generated feature IDs and cupids that we can then reuse in revision B, even though we made changes to the tolerance. And that's really important that we capture that data and not recreate it. But more importantly, I'm very happy because I am confident in that workflow that we just showed you from revision A to revision B. I am much more confident in this digital process, and I trust it much more so than I actually do anything happening manually. And I think that's the big win and the big takeaway from this proof of concept that I learned. I'd love to hear your feedback when we run into the Q&A session as well. I also still maintain traceability. And that's a pretty big deal. So no new programming, we're just updating, no loss of traceability, increased accuracy. So one of my favorite quotes is, "The only thing constant is change." So changes actually happen in our parts and our assemblies every single day. So I really wanted to dive into what the business value would be here, and I think there's probably a significant amount of business value in trusting this data, this digital data, through a revision cycle and diving into what that means. So having a way to streamline the changes by leveraging 3D digital data is a very worthy pursuit. Okay, I promised to come back around to QIF. Gave you a lot of data, a lot of code. Hope that was exciting to you. I find it extremely interesting to know that we can trace all that data in a very costly workflow and design process. So thank you all for listening to my story about change and how we can use QIF to help us out. It's available technology and framework. Some additional data here. You're welcome to go to QIFstandards.org and find out more, where we can always answer questions as well afterwards. Also, here's a little history lesson on where and when QIF came about. It's an evolution from the DMSC standard, which the DMSC also still holds. And if you'd like to know a little bit more, this presentation was actually adapted from a keynote that I delivered in March 2020, believe it or not. Yes, right before everything shut down. I was actually in Spain giving this presentation at MetroMeet. So there is an article that's publicly available if you would like to know more. And I think we have time for questions. So I will pass it back to you guys, and would love to hear some questions and feedback from the audience. Thank you.
Okay, thank you, Jennifer. That was really great. I have a question, and I'll get this kind of started. I haven't seen any questions come through chat just yet. But QIF is a standard. STEP is a standard. To people that may be uninitiated to this space, what would be the key differences between the two?
Good point. A couple of years ago, there was a presentation and work done. Martin Hardwick, who does a lot of work with STEP, did an interesting analysis between what is STEP used for, what is QIF used for, and I think also what is MT Connect used for as well. All standards in the manufacturing space, all developed to specifically, with specific charters in mind. But we're starting to see those kind of mash up and integrate together. So STEP standard began as a long-term archival and retrieval standard and has really blossomed and grown over time. There's huge amounts of work being done there. That standard is an ISO standard as well, 10303. And they started out with a certain set of data models and requirements and things like that. What I've seen it used for primarily is for geometry capture in hardcore manufacturing space, where they're actually, cutting chips, planning toolpaths of CAM machines directly from the geometry. Robust, being done every day today, the most prolific geometry translation standard for sure. They also have annotations and attribute capture as well that they're leveraging, and that's kind of where MT Connect comes into play, where that space is around doing in-process control and machine-to-machine connectivity, like CAM-to-CAM machine connectivity. So that's kind of where that integrates. And then if I shift focus back to QIF, that it sort of evolved out of a need for digital metrology and needing to capture those results that I showed you in the code. I needed to capture actual results in a first article inspection and relate them to the model-based definition. So now we certainly have a Venn diagram of all of those standards overlapping. STEP and ISO absolutely overlap, and there is an ISO harmonization going on right now to kind of figure out which ones are used in certain contexts and things like that. And I don't think there's any one answer. All of them are good because they're filling actual business value, and that's what I like to tell people to concentrate on is what's standard for what function in your organization is providing you the business value. And the reality of what I see is that you're probably going to use all of them in different contexts. Does that help?
I think so. I think that was a very astute response to the question. It was kind of a loaded question because I think that
I know
that a lot of people have the same same inquisitions as well.
Yeah, it's tricky. I mean, we always say, look, there's not one file format to rule them all. There's not one model to rule them all. You're just never going to get there. The reality is there's actually more file formats than we've ever had to deal with before, and that's a little overwhelming to people. But it's probably a reality that we need all those different file formats to capture the data about what we're doing in a particular part of the life cycle, you know, at that moment in time. And so there's always going to be a giant data set of machine readable data that goes along with that, you know, first engineering requirement model-based definition. So unfortunately, there is no easy answer. It is hard, it is messy, and it's complicated and overwhelming, and that's why we have to utilize all the technology we possibly can to simplify it.
Absolutely. We have another question. So when you were showing the QIF test results, in Rev B, exactly what IDs stayed the same?
So you'll see 2022 and 3318 stay the same. And from Rev A to Rev B.
Okay.
Is there another question?
Yeah. I don't have any more questions on the chat. If anybody else out there has any more questions, please put them in the chat and we can send them to Jennifer and have her answer them.
And if Curtis is on the line, I'd be happy to open it up to Curtis and his thoughts and feedback.
Yeah, Greg, can we bring Curtis into the panelist? There we go. Hey, Curtis, can you hear us?
I can hear us, but I don't know if I can talk. Can you hear me?
We can hear you.
Oh, great.
Hey there. Hi.
Well done. So the persistent ID idea is there's different kinds of IDs within the QIF. And the cupid is the one that we really enjoy, not only within the QIF, but even if it goes outside of the QIF, and you can use that as a reference to persistently to a characteristic, and typically that characteristic is pointing to, as Jennifer said, to an annotation or flatness or whatever type of call out you might have. And also you can use cupids for identifying unique feature as well. So the cupids are really worthwhile for if you need to get outside of the QIF normal framework and even bring it back in and reconnect things. And I think for those of us that where Jennifer was showing how you were ballooning the model or ballooning the drawing all the time, with the cupid and the characteristic IDs, you can also put human-readable IDs and persistent cupids on every one of those quote-unquote balloon-type items.
Right, and I think that's where we've really seen the value of, this is really a whole methodology, is to sort of clean up some of these messy steps that we have, and because there's just a lot of handoffs. I've actually counted them before, and depending on the part and things like that, it's anywhere between like 6 to 20 manual handoffs of data across, this picture of the life cycle, and that's just a lot. So we don't have to be that handoffy anymore. I think one of the reasons we have that many handoffs today is that all of the organizations have built these data silos. We've got one for engineering and one for CFD and one for drawings and one for manufacturing and another for quality and then another for supply chain. And then instead of, really all working together, we're just all recreating the data constantly over and over again. And so I really see model-based definition data as it flows through all those data silos, has a real kind of harmonizing effect where it can be the focal point or the beacon for everybody to focus on that data, and hopefully we have accurate data that flows through all those data silos.
Great. Okay, we have another question. Any suggestions of implementing this at an assembly level?
That's a great question. We should do that next. That should be the next prototype.
Yeah, that's good.
Yeah, it's very good.
Definitely the QIF MBD allows assemblies, but Jennifer is correct. I'm not aware of any prototypes at this point in time that's been shared with us on assemblies yet. So I agree with Jennifer. That should be our next prototype, is how does this look like in an assembly?
Yeah,
most
I
people
think
measure piece parts and then I guess they assemble them together, and it'd be interesting to see the use cases for that.
Yeah, and I think, Curtis, if we think about assemblies, of course, we don't really build parts, we build assemblies. But one of the use cases we've identified are inseparable assemblies, something like a weldment where, you don't necessarily do maybe a first article inspection on all the little components of that weldment, but you do it on the final assembly. And so inseparable assemblies tend to be the thing that we look at, I guess, next after we look at the component level first article inspection, would be inseparable assemblies. Or of course, there's always many use cases for assemblies that require assembly level geometric tolerance capture,
right.
Requirement capture.
Any other questions out there? Send in the chat.
Hey, Stephen, Annalise says that there are questions in the chat window somewhere that are not showing up. Annalise, I'm going to make you a panelist. Can you?
Yeah, she could just tell us.
Read out those questions.
Yeah, I just thought I saw several that weren't addressed yet, and I'm not sure if I missed that somehow. But there was one from Dan Glenn. Have you looked at the scenario where there's more than numerical changes, where the surface had to be recreated and has different internal IDs?
Oh.
Is there a way to reconcile that to the downstream artifacts without recreating them?
Well, thanks, Dan, for the hard questions. I can always rely on him for those. I think that's, again, another, I didn't test that, no. I only tested the dimensional changes and took a look at that in the code and created this story for you. But I think that's a great prototype to test next in addition to the assembly. I like it.
Okay, another one came from Dave Odendahl.
Oh,
go ahead, Curtis.
I guess it's kind of dependent on your modeling, if you changed and how you're connecting your features. So, you know, the QIF has features, and if the features are associated to the topology faces, and of course we know topology represents the geometry. So if the geometry changes, but the topology stays the same, then the feature is still connected. And so therefore, you would have still persistence of that cupid, of that feature, or any characteristics associated to that feature, because the connection from your feature to your topology face. Now, if your face gets blown away and and it never comes back, then obviously you're going to have an issue there. Or you create new geometry with new faces, then you're going to have to create new persistence, new feature types. Then in that case, you'll have new persistent IDs everywhere. So it kind of depends on your modeler and how, because I know certain geometric kernels will try to make sure the faces stay the same, even though the geometry changes.
Yeah, and that's probably a challenge for the interoperability vendors and a challenge for them to translate and validate, what would change and not change. I think it's a key point to bring up.
Right.
Yeah, actually I can comment one thing on that change report also would capture if there's geometry changes. I think this instance was showing the PMI specifically since that was the case, but you could show a map of a surface change in geometry as well if that were the case.
Yeah, definitely.
Yeah, the easy thing is you just change the size of the diameter, right? So the topology is always going to be the same. You just change the geometry. So everything should be persistent, and you still have the same IDs. But if you blow the hole away and recreate the hole at a different size, then you'll have some issues of persistence across a rev on the IDs.
Okay, so I'll capture another question I don't think was addressed yet from Mr. Odendahl. Where are you seeing the most interest? What industries, what parts of the QIF standard seem to be attracting the most attention?
Curtis, can I let you answer that one? Do you have an answer off the top of your head?
I'm going to see people interested in the model-based enterprise.
Yeah.
And being able to use models throughout the enterprise. And those that
I would agree.
Those that are trying to go to that direction.
Yeah, and really trying to maintain the traceability like we see on the screen here in a digital way, capture that traceability. I think that's really where I see it happening as well. And it's happening in all industries.
Right.
Yeah.
Now, without the MBD connection, obviously those that are interested in having a common format for measurement results, that would be a different group, a different discipline. Of course, the quality or people reviewing the measurement results. But I'm also hearing a lot from the quality engineer. They really like the fact that they can have a bill of characteristics that they can use for part of their planning. And the QIF has a QIF plan that helps you define a list of what needs to be inspected based on those characteristics. And that's easily generated. And then the QIF allows you to assign methods to each one of those, what needs to be inspected with how to inspect it. And of course, that's a role of the quality engineer as well. I do a CMM on this, I use a radius gauge for that, visual inspection for this, a thread gauge for that, CMM on this again, and of course the QIF allows you to accommodate that as well.
Okay, there was one other one I see here from Melissa Hughes. Can you go back to a slide that lists the ISO number related to QIF? Wasn't fast enough to write it down.
Oh, I certainly can, and I haven't memorized it myself.
23952 is Mark said it's 23952. That sounds correct.
Great. I don't even remember which slide I had it on. I'm sorry.
It's a tracker. It's the long DMSC to QIF.
23952. There you go.
And what's interesting is there's a questions about STEP and QIF. The same group that maintains the STEP standard, the SC4, TC184 at Subcommittee 4, is also the same group that harvested the ANSI QIF version 3.0 as a ISO standard. So there is some sharedness there at that level.
Okay, and the next one I see is from Mark Morrell. What is the current consensus for who owns the QIF in the product lifecycle? Who's responsible for maintaining control over its revisions?
Well, I can tell you this has been an interesting conversation to have, and I know Curtis has his perspective as well. It is typically what I see is engineering bringing it to the quality department and saying, this is what you should be using. That has some backlash from a kind of a people perspective. And so that kind of brings things to a head where the engineering and the quality department, back to those data silos, they really have to talk to each other more, which they're not accustomed to necessarily doing. And so it takes some special relationship building in order to have that conversation, because ballooning and first article inspection was all in that quality silo. And now with sort of, I've seen it move into the product definition phase, just because we want to get it into the source model. And so that becomes tricky from a people and a traditional organization perspective. Curtis, what are your thoughts on that?
Yeah, I think there's multiple owners. If you remember the life cycle, the lifesaver picture that we call it, where the QIF identifies a bunch of applications circled around the QIF library. And granted, a big chunk of that is more on the quality engineer and being able to report information back to anybody upstream in the life cycle. So there's a lot of people there. But if you start including the QIF MBD, and let's say you started in some native CAD system, and you want to exercise this persistence, you want to help metrology and your quality engineers and that entire element of your enterprise, then you are going to be creating what we might call an equivalent derivative that happens to be a QIF, and it's also an embellished derivative. Because when you go to QIF, you're embellishing and adding metrology features. You're adding something called characteristics, which is pointing to your annotations. So not only are you creating an equivalent geometry and equivalent PMI, but you're embellishing that derivative with all these new QIF capabilities, which brings lots of value. So you're going to have that embellished derivative model for all your downstream applications. Primarily, we're emphasizing the quality function of either manufacturing verification or product acceptance. But the hope is the earliest point that you add these persistence IDs, then that's where you can bring all these measurement results and feed it back to the earliest life cycle that actually introduces these persistent IDs, and then you can communicate that to that particular user, whether that's a process manufacturing engineer or the quality engineer or the design engineer. They'll have an opportunity to see that because of these persistent IDs.
I think that's an excellent point, and I love the word you use, embellish, because we see that too, right? Where engineering creates the source, and then the models evolve, derivatives are made, and we can do more with the 3D data than we have ever done before. But it is tricky to get people out of the mindset of thinking that's my job to do in quality, not your job in engineering. So therefore, you know, I don't want to take this on. And that tends to be a people barrier issue, culture barrier issue.
In my industry,
okay, one other thing.
Yeah.
Oh, sorry, go ahead. Go ahead, Curtis.
Yeah, I was just going to add, and you know, we've got a little 5 more minutes, I guess. But in my industry, we get an authorized part-defining model, let's say, and we cannot change that without approvals. So we'll take that model, and then we'll create the appropriate either equivalent derivative models, or in this case, we're making that equivalent derivative, but we're also embellishing it. And so the QIF allows us to embellish that. And now we own that as a production agency, as a quality engineer department, and then that would just be associated to that source model. And so if you have a part-centric product data management system, you can associate those models to each other, and
exactly.
Be notified if the source model gets changed, and that would notify you that, yeah, my embellished QIF model needs to be changed. Maybe we can automate that in the future. Maybe some people are. But I think part of this QIF is and our model-based enterprise experience is that we have this managed in a good product data management or product lifecycle management system.
Absolutely. A requirement, if you will, for all this digital data. Yeah.
Right.
Okay, I see just a couple more, maybe one comment and one question. So from Tony Ken, according to QIF version 3, the IDs like 3318 and 2022 are unsigned int. They're not cupid, which is a UUID. So maybe you want to comment on that, Curtis.
Did you say unsigned? Is that what it said?
That's what it says. I think she's referring to that it's not the 13 or, you know, it's a 4-digit character, not the actual cupid.
Right.
Oh, right.
Yeah.
Right.
I can explain that, or you can.
Yeah. No. Yeah. Go for it. I'll drop back to that slide.
So within the XML of the QIF, that's how you're communicating connectivity from a feature to characteristic or whatever. And so those are generated when you create a QIF just for speed. But there's a lot of key attributes or key objects that we allow for QIF allows for optional cupids. And so each one of those 3312s could have an optional persistent cupid. And like I said before, if you maintain those, then you can actually maybe temporarily leave the QIF and come back in and get reconnected, things like that. So,
and that's one of
those IDs are legitimate.
Right, and it's one of the things that you and I, Curtis, discussed when we were looking at this presentation together. And the evolution into QIF 3.0 allows for those options. Is that a correct statement?
Right, but I think those smaller numbers, those IDs, will persist within the QIF as long as you're uniquely in that QIF. So the number, you know, so you'll have that, but you can optionally add those persistent IDs.
Right.
But the QIF in itself may not use those cupids directly for its connections.
Right. Yeah, I realized for the purpose of this example, I really liked the 3178 and 2022 IDs because it made it easy to explain. Because if I'd had the entire thing, it would have been tricky to explain. But yeah, we've talked about that as having those options to have the full-blown UUID for the feature and the service profile separately.
Well, you would still have those 3-digit, 4-digit numbers inside a QIF file, you might just add for those particular items the cupids. So you wouldn't replace those 4 numbers with a cupid.
So you could have both, yeah.
Yep, you got both.
Okay, good. Well, then my example and learning example can stay the same. That's great. That's good news.
Exactly.
Yeah, no, that's good. Hopefully that helps answer the question.
Yes, I think there's one last one that I see here. In regards to this is from Mark Morrell again. In regards to the assembly context, it would be very helpful as a means to document in-process assembly tests, such as a high pod test. I'm not sure that's high potential, maybe. I'm probably not savvy enough.
Sure. We'll get 2 action items, Curtis. Look at it for assemblies and look at it what happens when you change the geometry and how that shifts.
And we have a third one. We need to invite Mark to be a participant in the DMSC.
Absolutely. I know Mark, so
okay.
yeah, good action items.
Okay, I think I got them on. I'm sorry if I missed anyone's.
Thank you, Annalise. I appreciate that.
Yep, no problem.
I had some technical challenges going into this, so hopefully it wasn't totally a mess. And you guys learned something new today.
Very much, Jennifer, and thank you, Annalise, for noticing the discrepancy with the chat.
No problem.
Okay, that brings us to the end. Thank you again, Jennifer. It was a great presentation. We hope to see you in future years of GPDIS. Our next presentation will be in 4 minutes, so we'll have a 4-minute break starting at noon Pacific time, 3 p.m. Eastern time, and we will see you there.
Thanks.